Good evening, everybody. Welcome to tonight's edition of the Triangle Area SQL Server User Group's main meeting. So we are in person once again at Tech Systems in Raleigh, North Carolina. Thanks to everybody who made it in person. Everybody who's not in person, you can always show up. I mean, it may be a little bit of a travel, but you can always show up. So unfortunately, our speaker who we expected to be here, Tracy Baggiano, she got ill, fell ill, was not able to present tonight. So she reached out to me and I said, all right, well, I'm going to be here anyhow, so I'll just do a presentation. And for that reason, we're going to do a talk on database normalization. Now, I did this for the advanced group about 2 years ago and have made some significant changes to the talk since then. So even if you've seen it before, there's still a lot of new stuff in here. As always, if you have questions, put them in chat or just shout it out. I will take questions whenever, but I will note that if you are chatting, laptop's over this way, so I may have to look over in an awkward way every once in a while just to see that everything is going all right. But anyhow, enough about that. Let's talk about me, my favorite topic. So my name's Kevin Feasel. I'm a data platform MVP out of Durham, and I have a one-man consulting company, Catalyxy Services. I also have a blog called Curated SQL, where every day I try to find and link to 5 to 10 interesting posts on topics all across the data platform space. So that's curatedsql.com. So the question is this talk right for me? And the answer is, if you're in chat, yeah, of course it's right for you. Why else would you be here? But have you ever believed any of the following statements? So first, normalization isn't relevant in the business world. This is just academic mumbo jumbo. Normalize until it hurts, denormalize until it works. I hate that phrase. Physical pain comes to me when people say this. The main purpose of normalization, you normalize because we want to minimize disk utilization. We want to remove duplicate data. Not the main reason. It's a good reason, but it's not the main reason. Database design doesn't matter. Just throw more hardware at it. Otherwise known as the cloud approach to things. Just throw more money at the problem. Eventually it'll go away. Turns out that at a certain limit it doesn't go away. This is relevant. And getting to third normal form is all you need. Everything beyond that is, again, academic mumbo jumbo. The final thing, third normal form actually matters. If you ever believed any of these things, you're in the right place. If you believe none of these things, you might still be in the right place. But what I want to do over the next hour or so is talk about database normalization, dive into the 2 most important normal forms, talk a bit about some other interesting normal forms, and cover critiques of normalization at the end, because they will inevitably pop up in a discussion. Now, normalization is a part of relational theory. It is a branch of mathematics. There is formal logic. There is technically a bit of math. I am going to move the camera. That is the third part of the warning here. I will try to minimize the learning curve. There's not going to be any heavy math. There won't be a quiz on this afterwards. The doors actually don't lock, so I can't force anybody to stay here. But at the end of the day, we are solving math problems. We are using logical analysis. It is a challenge for us that is a mathematical challenge. And some of the normal forms are mostly understood in an academic context, which means that we can't help but talk about this in math. Also, some of the interpretation of normal forms is weird in the sense of pointy-headed academic in ivory tower says thing in a paper. People interpret this as something radically different. And then we have folklore of what a normal form is. And this particularly affects one normal form that I'll talk about in a bit. But just wanted to note, all of this stuff does come from Chris Date's Database Design and Relational Theory book. 2nd edition, A-Press released it in 2019. Date is a very well-known person in the world of relational theory, does a really good job of explaining things in the book in a way that's quasi-academic. He'll slip into academic world for a little while, and then he'll get out of it and try to make it relatable to normal people again. And I've taken a lot of the ideas from that book and then applied it a little bit further. But our scenario, I wanted to have one common scenario throughout all the examples, and that is a music studio. So we're going to be responsible for managing artists, cutting albums, doing marketing, doing distribution. We're going to have to go back to like the late 90s, early aughts, because that was when music studios still mattered. But this studio is working on a centralized database system. Their application developers don't quite know too much about database design, so it is realistic in that way. And they would like our advice on how to do it the right way, which is maybe less realistic, but that's okay. So we're going to start with the basics. What is normalization? I don't think it gets more basic than that. That's probably the simplest question that I can ask here. So this is a set of logical rules and processes that we're going to follow to apply to data modeling. It is working off of a logical data model. So if you went to computer science programs at universities, you probably learned about logical data models and physical data models, where the logical data model is in some architect's head, and it's just a bunch of boxes drawn on paper, and then doesn't have anything to do with how the physical implementation is laid out. The physical implementation can be very different. Physical implementation is where we think about things like indexing. It's where we think about compromises. It's where we have to deal with the reality that data doesn't travel as fast as we want it to, and therefore we have to do something else about it. Certainly a lot more important 15 years ago, 20 years ago, when you had spinning disks, and I have very slow disk, and therefore I need to do something to improve the speed of seeks in data. Less important when you've got all-flash arrays or direct attached NVMe storage. So logical data models actually become relatively more important over time. And quick primer on terminology that we're going to use over the course of the night. So we typically are used to thinking in terms of tables, of rows, of columns. There are some terms that I'll use which are very similar, but are a little bit more mathematically sound. So at the highest level, we have this notion of a relational variable, and we also have a related notion of a relation. This is relational algebra. This is the basis of relational databases. And relations here doesn't mean we join things together. What it means is a relation is a collection of a heading and a body. And specifically, a relation is also including the tuples, the rows of data, at a particular point in time. So a relation has our heading. Our heading has attributes, column names, and data types. Our tuples are made up of a collection of those same attributes, those same data types. And that's our relation. That is at a point in time. Now, if you think about something that's more generic, something that's more across all of time, we have this notion of a relational variable, or a relvar. So if I say I have a table called employees, what I'm talking about here is either this table at this point in time, on this day, at this hour, with these rows in it, or I'm talking about more of the concept of this is my employees table, where I don't necessarily know what data is in there. I don't care what data is in there. I understand that it's going to change over time. And to separate these two notions, we have two different terms. We have relation and we have relational variable, or relvar. So I'm going to use the term relvar a whole lot during this session. Just think of it as a table, but I don't necessarily care what data is in there. So what are we going to do with normalization? Why do we normalize? Well, removing redundant data is in fact a reason to normalize. So that one of the questions of should you be in here, that is actually a valid reason, but it's not the only reason. A really good reason is to fix incorrect designs. Designs that are known to provide bad information, that are known to cause problems down the line for people. We want to achieve a design which is a good representation of the real world. So our model is only as good as the underlying reality which it's trying to support. All models are imperfect representations of the real world. There are always going to be simplifications. They're always going to be wrong. So all models are wrong. Some models are useful. Normalization helps us come up with more useful models. And simplifying how we define and enforce certain types of integrity constraints. Not all integrity constraints are going to be covered with normalization, but some of them will. And by following these rules of normalization, we automatically get some of these integrity constraints. Other ones become trivial to implement. So it's a way of making our lives a bit easier. There are a lot of normal forms. This pyramid represents several of the normal forms. There are more that could be on this pyramid. However, most of this pyramid is not particularly relevant to practitioners. And I instead of thinking of this as a pyramid where you're building up on prior normal forms and getting more complicated answers, I like to think of it more as a tier list. So we have our S tier, Boyce-Codd Normal Form, Fifth Normal Form. Those are the two that if you walk out of here knowing what these are and how they work, you're in great shape. Those are the only two that you really need to know. A tier, the Sixth Normal Form. Sixth Normal Form is a really good normal form. It's uncommon, but there are specific circumstances in which I like it a lot. The B tier, these are ones that you should know about, but are overrated. First normal form and fourth normal form. First normal form, very much overrated. We do have to talk about it because it is foundational, but it actually doesn't give you as much as you think. C tier, D tier, not even going to talk about them. Second normal form, third normal form, those are D tier. They are at the bottom of the list. I do not care. I could not care less about second and third normal form. And by the time we're done with our first couple of sections, you'll see why. So let's talk about our B tier normal form of 1 and F. So first normal form is about key rules and the shape of these tuples. So I mentioned a tuple, which common parlance we think of as a row. So suppose we've got some relational variable with a heading that has some attributes. Basically columns with names. They have data types, and therefore all tuples must follow the heading. And they have to have one value of the appropriate data type for each attribute. In other words, we want an example of this. So we have artists, we have albums, and we have years of release. So for Tsunami Bomb, they released 3 albums, 2002, 2004, 2016. Then in 2019, they released a 4th album. In order for me to add a record to this album table, it's got to have an artist, an album, and a release year. Artist must be of type character, or varchar, or invarchar, or whatever. Album must be a character type. Release year must be an integer type. I cannot insert dog or something that is not an integer. So I'm already constraining what I can put into this relational variable because it's got to have this exact form. So rules on first normal form. Number 1, new tuple needs to match the existing rel-var's heading. You can't insert rows with like 8 columns when you only have a table of 7 columns. Tuples must have values for all attributes. Null is not a value. So this is an important thing to hit up. Null violates first normal form. If you have null on a table, it is not in first normal form. That is something that is a little controversial, but null is the absence of a value. It is unknown. No duplicate tuples are allowed. This is coming back to relational theory. It's coming back to set theory. When you have a set is unique. You can't have 2 elements that are exactly the same in the set. They have to be different somehow. That's just the nature of a set. It's automatically distinct. So in a relation, in first normal form, we can't have duplicate tuples. Attribute order does not matter. So I showed you an example that had artist, album, year, but I could query that album, artist, year, or year, album, artist, or whatever. I can insert into a table year, album, artist. And if you think of this in T-SQL terms, I can insert into a table. As long as I define the columns in the column order, it doesn't matter that this is not the order that it's laid out in the table definition itself. Doesn't matter at all. So attribute order doesn't matter. Tuple order doesn't matter. This is why we, in a T-SQL query, a select query, unless I expressly order it with an order by clause, I do not get a guaranteed ordering. There is no ordering on relations. There is no ordering on sets. Technically, throwing an order by clause changes the nature. It's technically no longer a set. It's some other mathematical term. But as far as we care, how we insert these tuples doesn't matter. And all attributes are regular. So they have names, they have types, they're not hidden, they're not special types in some way. Like Oracle, actually this tends to be a real killer if you're getting really pedantic, because tables in Oracle have hidden identifiers. Technically, they don't follow first normal form. Some tables in SQL Server, if you have a graph table, they have hidden identifiers. There are some tables that do have hidden columns. And if you have hidden columns, if you have columns without a type, if you have columns without a name, you're no longer in first normal form. And where I want to get to this is that first normal form is either trivial or impossible, depending on how pedantic you want to be. Because it's trivial in the sense of every relational database product, if you create a table, it is in first normal form. Pedantic in the sense that no relational database is ever going to be in first normal form. Realistically, you can swing however you want on that one, but effectively, I'm going to pretend we're all in first normal form as long as you don't have any nulls. If you have nulls, get out of here. Now, it's pop quiz time. This table right here, is this in first normal form? So in case it's difficult to see, we have an album with an ID and an album name. We've got a runtime, we've got a year release, artist ID and name, artist ID 2, artist name 2, genre ID and name, genre ID name and ID 2, genre ID and name 3, and then some binary cover art. So is that in first normal form or not? Anders says no. Anybody in here want to hazard a guess?
No. Second no.
All right, we're getting a lot of no's. It is.
Oh, no.
So this is one of the things that people get hung up on, is the idea of repeated sets. And usually you look at this and you say, this is a bad design. If I asked, is this a bad design? The answer is absolutely.
Yes.
People get hung up on this idea of genre 1, genre 2, genre 3, that, oh, this isn't in first normal form because we have repetition. The definition of first normal form doesn't say anything about repetition. It simply says we have non-nullable, none of these are nullable. They have to have a header that's defined as a data type and an attribute name, and any tuple has to match that. This is all that we have for first normal form. People have added on over the years other things. Actually, Date is one of the people who's added them on, and then he later on said, yeah, I was wrong. So there's been a lot of mixed messaging, and in the folk understanding of first normal form, you get these notions of repeated sets. I had a slide a long time ago in an original normalization talk where I included it. Artist ID. Artist ID is just a artist ID is just a key to the album's artist. You have possibly, actually, definitely 2 artists here. That's one of the problems with this table design, is for it to be first normal form and not nullable, every album must have exactly 2 artists. Kind of dumb, but you know what? It's still technically not a violation of first normal form if our data model supports it. Let's say our company only does matchups of 2 artists and combines them together on one album. In that case, this could actually make sense. Yeah, I mean, because I'm in example world, I get to make up whatever I want. So it can work out. But that first normal form, not very impressive, not very interesting. So the entire record has to be unique. Yes, the entire tuple, or the row, is unique. And oftentimes, what we do is we use a surrogate key. Technically, surrogate keys shouldn't be considered. Surrogate keys are not the thing that makes a record unique. They are a thing that is applied after the fact on a unique record. But aside from that, every row needs to be unique, and that's how we're in first normal form. So now let's talk. This is worse than the books online samples. So Anders, this is intended to trick you. Books online is just not intended to trick you. They're just not very good. So now let's talk a little bit about Boyce-Codd Normal Form. Boyce-Codd Normal Form is one of the two most important normal forms. It is probably the most important normal form, but I don't want to go out that far. It is going to protect you against a variety of data anomalies. So update anomalies, certain types of redundant data, and missing data. So let's say we've got some data. We've got release dates, or we've got dates that band is in studio, the band that's in there, the album that they're working on, the genre that they're working in, the studio that they're in, and the manager of that studio. So we've got a few people who are coming in. They are doing some recording on these days. And let's say life changes, life happens, and we need to update the data. So for example, we now have a new manager, Lindsay. She's taken over Studio A from Marie. And we successfully updated 2 of the 3 records, but because there are 3 records with that manager's name, we kind of missed one. So this happens a lot when you have like your data in an Excel spreadsheet or in an application which is like an Excel spreadsheet, and you just paste it out like this. This is a problem. Redundant data. So we had one of our bands, they had to cancel on a day. They couldn't come in to record, and we decided we're just going to have the other band come and just do the whole day. Well, the problem is that by updating this first row, we now have a duplicate. Duplicates are not in first normal form. We can't have that. So that's a problem. Missing data. We had a Studio C, but nobody knew about it because we didn't have anybody booked in it. So the question is, how do we show that Studio C exists? Using our data model, we have to put in something dumb like a placeholder record that says, oh, nobody's in here in Studio C. But that's absurd. This is not real information. This is not an artist, album, and genre. It is just a hack around a poorly designed system. So these are the types of problems that we run into when things are not in Boyce-Codd Normal Form. We can define Boyce-Codd Normal Form in 6 words. All functional dependencies have superkey determinants. That's it. It's no big deal. All functional dependencies have superkey determinants. And then the next question is, what's a who's what now? And so let's talk about these terms. There's only 6 words. It's only going to take us like 20 minutes. Superkey. A superkey is like a regular key, but it wears its underwear outside of its pants. This is a unique combination of attributes, not necessarily the most parsimonious. So in other words, let's say that recording date and artist is a key. We can guarantee uniqueness with a recording date and an artist. Recording date on its own is a subkey. It is part of a key. Recording date, artist, and studio is a superkey. The key itself plus something else. So superkey is key or more. Next up, functional dependencies. Let's say I've got a sound engineer, and at a studio we have producers and we have sound engineers. And who the sound engineer is will be determined by the studio and the producer. So producer Janice in Studio A, her sound engineer is Sam. Randy in Studio B, her sound engineer is Edgar. Janice in Studio A, again, is Sam. Tamika in Studio C has Sam as the sound engineer. So what would we learn from this? There's a couple of bits. Number 1, whenever we see studio as A and producer as Janice, we know sound engineer is Sam. In other words, studio and producer, and I let the word slip already, they determine the sound engineer. So this combination of studio and producer is the determinant for the sound engineer. And I can write this in mathematical terms using a single arrow to the right. So the things that determine, the determinant, single arrow to the right, the thing that is determined. And these are functional dependencies. Functional dependencies only go one way. And that was why I had the example with Sam and Tamika in Studio C. Because Janice and Studio A lead to Sam doesn't mean Sam leads to Studio A producer Janice. It is not a two-way relationship. It is determined one way. So in other words, like a mathematical function where you can have, if you have a simple mathematical function where f of x equals y, you can have you can have multiple points of x that have the same value of y, but you cannot have multiple values of y that have the same point for x. So this is our going back to algebra days portion of the show. Basically, when we have this functional dependency, we have a declaration that I expect whenever I get these inputs, I will always get this output. Now, figuring this out in practice can be difficult. And there are two techniques that I'm going to bounce off of here. One is ask someone who knows. And of course, now you have to find someone who knows. So that's the next problem. But in the academic literature, they're like, that's a practical implementation issue, not my problem. So you discuss business rules, you figure out what is it that you know, you try to understand, okay, so you have producers in studios, they always work with sound engineers, and because of the way that the sound engineers are hired, this is how it works out. Or the other approach, the reverse approach, is we review the existing data and just try to see where we've always got matches. So figure out columns whose values always match up in some way. Now, functional dependencies, they have to hold. They are required to hold. It can't just be a sometimes thing. It can't be like sound engineer gets determined by studio and producer, except when it doesn't. So this is mathematically required, which again makes things difficult. It makes it a lot harder for us to really nail down what is a functional dependency and what just is happenstance. So going back to our definition, all functional dependencies have superkey determinants. What can we say about this? Well, a superkey, and maybe there's something more to it. Functional dependency is that strict relationship between attributes. You have some attributes which determine something else. And a determinant is that input for the functional dependency. So in other words, any functional dependency, any of those relationships, must have as the input a superkey of the table itself. If you are in Boyce-Codd Normal Form, you are guaranteed to have none of the anomalies that we showed. The update anomalies, the redundancy anomalies, none of these problems. So how do we get there? And the answer is that there's an approach, and the approach starts from creating a mega table. The idea of the mega table is you have all of the columns that are possibly related to the problem, and you just slam them together in one big table. And then you get all of the functional dependencies. So we have here digital marketing campaigns for our albums. And my digital marketing campaign has a single key on campaign ID and audience target ID. So that is the thing which makes this table unique. The combination of those two attributes makes this table unique. But we also have some functional dependencies. So the campaign ID determines the campaign name, the campaign owner name, the agency ID, the maximum budget, the minimum bid. The agency ID determines the agency name and the take rate. Audience target ID determines the targeted age range and genre preference. So the whole idea here is that we're doing some sort of targeted advertising on Facebook, on Google, on Twitter, whatever, and we're going to say, for people who are interested in this particular genre of music, here's a new album that we're bringing out that's right in your age range, it's right in your genre preference. We want you to see this, we want you to click on this and potentially buy it because we think you're more likely to buy it. So we're willing to pay more for your click than for somebody who is way outside of the expected range. So then the combination of campaign ID and audience target ID determines the audience bid modifier. So that is how much of a difference are we going to get based on how closely you hew to the expected preference of this particular album. So we want to figure out, are we in Boyce-Codd normal form? Well, ask the question, are all determinants candidate keys? And here are our determinants once again, and the answer is no, because the only candidate key, the only thing that makes this table unique, is the combination of campaign ID and audience target ID. The only one of these determinants that is a candidate key is the one at the bottom. For all of the rest of them, they are not super keys. Campaign ID and audience target ID are sub keys. That's not enough. It needs to be the key or a super key. Agency ID, not even related to the key. So, okay, how do we handle this? Step 2.5, Heath's theorem. So we have to talk a little math. There's a concept, Heath's theorem, because in order to get tenure, you've got to come up with a theorem. So everybody has to come up with one. Given a relational variable R, and it's got some components, which we'll call x, y, and z. And in this case, x, y, and z can be the entire combination of all these columns. So x could be like campaign ID and audience target ID. Y could be audience bid modifier. Z could be all of the other columns. Let's not get hung up on you have to have exactly 3 columns or anything like that. But you've got components. You've got x, y, and z. And you have some functional dependency, x to y. We can break this relational variable into 2 separate relational variables, xy and xz, without loss. And what I mean by without loss is I can break that out into 2 tables. I can bring it back together into 1 table. We get exactly the same rows as if we never broke it out. We have no fewer rows. We have no more rows. Both of those would be problems. And the data that's in here is exactly the same. So, okay, Heath's theorem says that what we can do is take a table and break it out into multiple subtables if we have a functional dependency and we have the remainder. So we have a functional dependency on agency ID. Agency ID takes out agency name and take rate. So what we can do is we can break that out into a new table called agency, which has the ID, the name, and the take rate. So agency ID is our X. This is our Y, agency name and take rate. And Z is everything else. So we have X and we have Z. And we've successfully broken this out. Then we can repeat steps 2 and 3. Are you done yet? No. Okay, let's take the next functional dependency and break it out. Campaign. So we take campaign ID, we take all the things related to a campaign, we pull it out, we realize this is all related to campaigns. So I'm going to call that thing a campaign. We take out all of the determined columns from our remaining table, and we do it again. And we keep going back to this. Our remaining functional dependencies. We have one on audience target ID. We have one on the combo of campaign ID and audience target ID. Not good enough. We still need to do it one more time. Take out audience target ID. With it, target age range and genre preference. And then we end up with a set of tables that looks like this, where we have our campaign that has all the campaign stuff, including the agency ID. We have the agency table that has ID, name, and take rate. We have the audience target table that has the targeted age range and the genre preference. And then we have what's left over, which is campaign ID, audience target ID, audience bid modifier. And I can look at that and say, that's not a DM campaign. That's actually a campaign target. So the process of doing this has helped me come up with not only the right way to break this out, but also the fact that this was misnamed. That had a wrong name. And now I've got a better name for it. So in the process of doing this, iterative measures, we've come up with a much better data design that is not going to have the types of problems that we saw earlier. And that's Boyce-Codd normal form. Now, this is the point where if I had my camera just a little bit lower, I would sit down on here. But this is where I'd say, hey, why am I so down on second and third normal forms? And the answer is Boyce-Codd normal form is the general implementation of second and third normal form. Second and third normal form are a specific case. Boyce-Codd normal form is the general case. If you're in BCNF, you are guaranteed to also be successfully in second and third normal form, and there are other problems that you have solved. So for that reason, second and third normal form, completely irrelevant as long as you understand Boyce-Codd normal form. So next up, fifth normal form. Fifth normal form is the other really important normal form. And what Boyce-Codd is to functional dependencies, fifth normal form is to a thing called join dependencies. Join dependencies are a lot harder to define. They're a lot harder to understand. They're a little bit mushier in terms of implementation. A relational variable is in fifth normal form if and only if every one of these join dependencies is implied in the keys of that relational variable. So let me try to talk about it in a little generic example, and then we're going to get a couple of more specific examples, and hopefully things will tie together. So let's say we have X. X is our entire heading. So it's all of the columns, it's all of their data types. And if I can split up X in any way such that this split can be non-loss decomposed and then recomposed, then this is a join dependency. So unlike a functional dependency, this isn't something that I can necessarily a priori come up with and say, yes, clearly these columns come together, and therefore we have a join dependency. Like I kind of can with a functional dependency. Sometimes you can look at that and say, well, yeah, of course the campaign ID is going to determine the campaign name and the campaign owner. Boyce-Codd normal form equals do it so it makes sense. Kind of. And that is one of the nice things about normalization is it's a logical process. As long as you're willing to think logically, you can usually get through many of these things. Now, thinking logically can be hard, but if you do it, it works out pretty well. So, all right, quick example. Let's say that I've got warehouses. I've got some warehouses, and I've got a warehouse ID, the general manager of the warehouse, the city it's located in, and the property tax rate of the city. Just an average property tax rate for that city. I have two functional dependencies. Number one, the warehouse ID determines the general manager in the city. So we have a general manager of the warehouse. We have a city in which the warehouse is located. Number two, the city determines the property tax rate. I know there's specifics, but whatever. For my example, Chicago has a property tax rate of 4.8%. Lafayette has one of 2.1%, Lexington 3.3%. So are we in Boyce-Codd normal form? Counting on you, Wayne. You don't think so? You are correct. So Wayne is correct. We are not in Boyce-Codd normal form. The reason is we have a functional dependency, city, which is not part of the key. The key is warehouse ID. So that functional dependency really belongs on its own. We could split this out and have our warehouse that has a general manager and a city, and we have a city that has, that's a typo, that should be property tax rate. So by doing this, we remove the risk of updating the property tax of Chicago to 5.2%, but missing it in this record. Basically the same reasons we would do any type of Boyce-Codd normal form example. So what we were able to do here is take some of these attributes and split them out. I mean, we've seen this already. This is just another example of a functional dependency. And it is true. All functional dependencies are join dependencies. But join dependencies include things that are not just functional dependencies. So that's where we get trickier. Like Boyce-Codd normal form handles functional dependencies. But then there's this other world that's beyond functional dependencies that we still have to care about. So we may be in Boyce-Codd normal form, but not in fifth. Oh, no.
Yeah, I think you stepped on something.
Yeah, I did step on this. Okay. That's what I get for wandering around. All right, good. So, meanwhile, the streamers didn't see anything, but that's okay. That's the power of the coupler. So, you can have non-functional join dependencies that are not key-based. And let me talk to you about an example. So we've got artists, we've got albums, we've got countries in which those albums are sold. And then, so we've got the one album from my favorite Danish sextuplet, Psychobilly sextuplet specifically. And we've got sales in the US and Denmark. We've got a combo from two bands, Band 1 and Band 2. They're creating an unnamed future album. It's going to be sold in the US and Canada. So I've got these 4 rows that represent Band 1 and Band 2, Canada and the US. As you imagine, if we had a third country this is sold in, we're going to have several more rows. We're going to have 2 more rows. If we have a third band that we bring in on this album, we're going to multiply the number of rows. So we can already see there's kind of a problem here. This doesn't feel right. But here's the thing. The relational variable has a key of artist, album, and sales country. So in other words, this is in Boyce-Codd Normal Form. As far as BCNF is concerned, this is perfectly fine. But it should feel weird. It should feel like this is not correct. And that's because there is a join dependency here. There is a way that we can split out this data without losing information. And specifically, we can split out album and artist, album and sales country. And by doing that, we're going to break this ternary relationship into 2 relational variables. This is a join dependency, and it gives us an easier to understand model of our data that is not going to have to worry about if I add a new record, like I add another country, I need to have 2 rows here. This is where you do a bitmap for countries. Anders, get out of chat. So by breaking this out, we now have a simpler example. If I add a new band to this album, it's no big deal, it's 1 row. If I remove a band from the album, it's no big deal, it's 1 row. If I add a new country, again, no big deal, it's 1 row. Our goal here is one change of the data should be 1 row that gets changed, not multiple rows that get changed. That's kind of a point that we're trying to move toward. It's a logical consequence of appropriate normalization. Now, there's another more convoluted example that I'm going to have to cover, and that is called the connection trap. And the connection trap, so think of this idea. We have a store. We have a music store. So again, it's 15 years ago. They stock albums for a particular genre, and they stock albums for a particular artist, and that artist performs in that genre. If we have all of these 3 rules, then we know that our store is going to sell works in that genre from that artist. And I've got to stop stepping on that. There we go. All right, I'm gonna move over 1 step this way. So this is known as a symmetric constraint. The idea here is that if we have this in play, a change in one of these is going to necessitate changes everywhere down the line. If it does not apply, we can potentially fall into something called the connection trap. The idea here is that if there is no symmetric constraint, we are going to need all 3 of these attributes in a single table in order to determine what information is true or not. So we have 2 stores, and one store sells punk rock and progressive rock. The other store sells indie, or twee, but I didn't include twee on here. And we've got some artists. We've got artists, 1 punk rock band, 1 prog rock band. We've got 1 indie band. And if the symmetric constraint does not exist, we are in 5th normal form. However, if there is a symmetric constraint, we can break this down further. So if we have a symmetric constraint, or in other words, a rule in which a store is going to sell all artists in a particular genre, then we can decompose this into a 3-part relationship. So we can have store and genre, genre and artist, store and artist. And the combination of those 3 tables, we can bring it back together and get the original data set. So we have no connections trap here. We have our stores and we have our genres. So one store sells punk and prog, one store sells indie. Genre and artist, we have store and artist. As long as the constraint holds, everything is fine. But something that, what if Bad Religion, a punk rock band, creates a prog rock album? And it turns out they did back in the early 80s. What happens is nobody buys it, people get angry that they changed their style, and then they go back and have to go back to punk rock. Real life sad story. But with no connection trap, they're selling this prog rock album, which apparently you can only get in vinyl at this point. And that means that our store that sells prog rock and that sells Bad Religion has to carry this album that nobody bought. But apparently it was okay. I've never heard it before. So Music Everywhere has to sell their prog rock album because of the symmetric constraint we have imposed. But now, let's go back and let's say, no, there is no constraint like that. The store sale, the general manager at the store or whoever the buying manager decides what they're going to stock versus some rule that says, no, you have to sell this. So the only results we should see are these 3. Because the buying manager said, I control what to buy and sell. Just because our store sells prog rock and punk rock doesn't mean we have to sell that particular album. So we break this out into 3 tables because we see this is a ternary key, and we say, well, ternary keys should be broken out into 3 binary tables. It's obvious. But is it correct? And the answer is, well, we're seeing that they are selling prog, and they do sell this artist. And therefore, because this artist has an album, if we join all these tables together, we're going to get a row that says Music Everywhere sells this prog rock album by Bad Religion. But that's not true, because the truth is they only sell these 3 combinations. So we've added a new combination. We have created a phantom row, a phantom insert. That correct. That is ultimately the symmetric constraint. There is a business decision whether or not it should exist or not. And based on that business decision, either this 3-table setup is perfectly fine if the constraint exists, or it is perfectly wrong if the constraint does not exist. So why bother? If it feels like overkill, if you're like, 5th normal form is pretty high, I can barely count on that with my hand. Here's a couple of reasons why it can be important. And in a lot of cases, you will see people who go into normalization basically say, 5th normal form is like head in the clouds stuff. I disagree. I fully disagree, because with no composite key, you're already in 5th normal form if you're in Boyce-Codd Normal Form.
You get into data integrity at that point.
Right. Yeah, so you get into data integrity here. So composite key just means a 2-part or 3-part or 4-part key. If your key is 1 part, 1 column, you're already in 5th normal form if you're in Boyce-Codd. So you're already good. Any relational variable that is not in 5th normal form can have deletion or insertion anomalies. That is, records that, strangely enough, disappear. Like, I had this thing in here, but when we broke it out into 3 tables, that row disappeared. That row didn't disappear, it's just you structured it wrong. Or we had suddenly selling Bad Religion's progressive rock album. Oh, it's great until you run into issue with too many joins to get data back together. That's, yeah, well, we'll really get to that in the next one, Anders. Symmetric constraints, they are not extremely common. But there is actually a fairly common variant that we want to talk about, and that is 4th normal form. 4th normal form is actually an anachronism. 4th normal form is a subset of 5th normal form. It's just that the paper for 4NF came out before 5NF, and so it got its own special normal form, and then people were like, wait, actually, here's the general case. That's just a special case of it. Therefore, 4th normal form is easy to explain, easy to understand, much less relevant than 5NF. You are in fourth normal form if and only if every multi-valued dependency of R is implied in the keys of that relational variable. So what do I mean? A multi-valued dependency is a joined dependency with two components. So I already showed you an example of this, album sales. We had album sales that had artist, album, and sales country. If you have an artist that sells an album and sells it in a country, each album has a set of artists, one or more artists. Each album is sold in a set of countries, one or more countries. And for each album, there is a tuple for every combination of artist and sales country. So we have, going back to this example, well, this is a multi-valued dependency. We have basically two independent subsets of data that we have smooshed together and that we should pull back apart. Specifically, album and artist, album and sales country. And you have to do it in that order. You can't take it like sales country and artist and expect to get anything good. So it's got to be in this order. You have to understand the data. You have to understand how the splits occur. And in 4NF parlance, they use double arrow. So functional dependency was a single arrow, and then you had double arrow for 4NF. But really, this is the 5NF join dependency definition of it. Basically, split it out into two tables, and you're going to avoid some problems. The way that we can split it out is because of Fagin's theorem, totally different from Heath's theorem. Fagin's theorem says that if you've got X, there's a multi-value dependency on Y and Z, then you can split this into XY and XZ. You can break that out into two separate tables. Everything is hunky-dory. So what this prevents, you don't need multiple copies of the same record. So unnamed future album only needed one row per artist per country. But what if I forget this row here with band 2 and sales in the US? We have bad data at that point because unnamed future album is definitely selling in the US. It's definitely selling to band 2, so we need this row. But it's easy for our application to miss it or for somebody to update it incorrectly. As we get more and more of these, like if I have 5 bands on the same album that sells in 80 countries, I need now 400 records. And I need to update 400 records every time I'm doing something across the entire album. Like I changed the name of the album, I need to make sure I update 400 rows. If your application doesn't know how to handle that appropriately, you could easily end up with some records that have the wrong album name. Updates, probably you're going to need to update multiple rows. Deletes, probably you need to delete multiple rows. Like, well, that band got canceled, so we're going to need to remove them from the album. So we need to delete possibly multiple rows. And that can be an issue. So now let's talk sixth normal form. Let's talk about the normal form that's going to cause Anders all kinds of pain in terms of joins. You are in sixth normal form if all join dependencies which hold an R are trivial. Join dependency, we've got subset of attributes. Trivial means we've got one non-key attribute. So we've got the key, and we have one additional thing. So let's give you an example. Going back to our original example, kind of a simplified version of it, the quiz. We've got an album ID and a name. We've got a runtime. We've got a release year. We've got artist ID 2, genre 2, genre 3. And our natural key is on album ID. This is in fifth normal form. We are in Boyce-Codd Normal Form. We have a non-composite key. We are in fifth normal form. We are in great condition, except I can make it a little better. I can define this in sixth normal form by taking every one of these separate attributes and making it a different table. So I could have a table that includes the album ID and the album name, a table that includes the album ID and the runtime, a table that includes the album ID and the release year, and on, down to a table that includes genre ID 2, a table that includes genre ID 3. I'm already looking over to see if the pain is here. I had one application where street number was foreign keyed. That's my official answer. Okay, so do we actually need sixth normal form? And the answer is a hard maybe. So if an attribute always has a value, Probably not. By the way, this design up here is actually pretty similar to the data vault structure in data warehousing. Data vault is a lot more popular in Europe than it is in the US, but it had its popularity in Europe. And essentially you had a whole bunch of essentially 6 normal form that was then brought together in views to give you more of a, they called it 3rd normal form, but give you more of a classical 5th normal form structure. So if you always have a value, it's probably easier just to cluster them together. Don't go into 6 normal form. However, if something's missing, we could break that out into 6 normal form to avoid null. Up to this point, we haven't had a good way of saying, what if I really do have an optional attribute? What if, like runtime, I don't always have a runtime value? How do I solve this problem? Up to this point, up to 6 normal form, we have not had a solution. 6th normal form gives us a solution. We create a new table that includes album ID and runtime. And if you have a runtime, you insert a row. If you don't have a runtime, you don't insert a row. And then you left out or join to that table, and you get back your result set. Your result set can have null in it. You can send null out to the application because at that point, it's that poor fellow's fault, problem to deal with versus yours. But you never have a null stored in your system if you follow that rule. So if an attribute is part of a nested set like genre, genre 1, genre 2, genre 3, and we don't care about the ordering, because with nested sets you really don't, it's a set, you don't care about the ordering. We can unpivot those into one table and have a genre table. So now we have an artist genre. And that makes life a little easier. This is again getting back to some of the stuff that we thought about in 1st normal form. Really, we go to 6th normal form to get what feels like the appropriate implementation. So what I'm suggesting at this point is we might have a table that has album ID, album name, release year. We have a table that has album ID and runtime. We have a table that is album ID and artist ID, and we could have more than one row in here, obviously, because we have more than one artist. Same with genre. The other case where this can make sense is intervals. Intervals of data, stretches of time. So 6 normal form helps us understand temporal data. Like let's say we've got tours. So we have 2 bands, they're touring different cities over different ranges of time. And so Bad Religion is in London for 4 days or 5 days or whatever. The Horror Pops are in Paris for 1 day, and then they're in Athens for a few days. So they're on tour. Well, let's say I've got a slowly changing type 2 table. So I've got a headliner artist, I've got a warm-up artist, a city, a start date, and an end date. And so our headliner in London for the first 8 days is Bad Religion. Our warm-up artist is Rad Religion, which actually is a real band. They were a cover band, obviously. In their own guise, they actually were pretty good down in Gainesville. But anyhow, for 8 days, they're going to be there. And then the Deviates are in London for days 9 to 14. And then they all move to Paris for the last few days. Horror Pops are in Athens for 17 days with the Chop Tops as their warm-up artist, another psychobilly band out of San Diego. Necromantics, my second favorite Danish psychobilly sextuplet, is in Athens for day 18. So I can break this out into 2 non-redundant relvars. I could break this out into headliner and city and time interval, headliner and the warm-up band and a time interval. And by breaking these out in this way, I have fewer rows. So I have, instead of 5 rows in any table, I've got 3 rows over here and 4 rows over there. I have a simpler solution. I don't need to have a new row every time one attribute changes. If I change the warm-up band for subsequent days, I don't have to change the city unless they actually move to a different city. And I can bring these back on the intervals to get my final results. So to visualize this interval, we have here, I'm going to show just the screen for people on camera there. So we have just the interval, and for Bad Religion in London, they're there for 14 days, and they're in Paris for 3 days. The Horror Pops are in Athens for all 18 days. Now we have their warm-up band, And so 8 days, days 9 through 17 for the other band. We have 17 days for one band, 1 day for the other warm-up band. This is our way of seeing what those intervals look like. I can unpack and repack that data. So if I pick Bad Religion and I want to look at sort of getting back to that slowly changing type 2 dimension shape, I can take all of these rows, I can break it out, unpack them, unpivot everything so that I have 17 rows that include an artist, a warm-up band, a city, and a day. And then I can find all of the duplicates and smash together the ranges. So Bad Religion with Rad Religion as their warm-up band in London for the first 8 days, and then the Deviates for days 9 through 14, and then they go to Paris for 15 through 17. This actually gets us back to our type 2 slowly changing dimension, but we don't need to store the denormalized data. We can store it in 6th normal form with these intervals that are packed together. And intervals are technically still considered part of the key in this case. So we don't have to worry about, oh, we have 3 columns. You can have 3. Basically, your interval is the artist and the date range. And then our second attribute, our other attribute, the warm-up band or the city. So that's 6th normal form. That's when it can be important. It's not very common, but it's useful sometimes. So I want to wrap this up with some normalization discussions, like data warehousing. I just talked about type 2 slowly changing dimensions. Well, relational theorists tend to poo-poo data warehousing a lot, especially the Kimball model, because as a general purpose relational data warehousing model, as a general purpose relational model, the star schema that we see in data warehousing is awful. It is, however, a really good model for data warehousing in specific circumstances, and Kimball lays it out in his book. You have one and only one process to write the data. The model is a proper model of business processes and business understanding. The facts represent measurements of things. Dimensions represent information about things. So your fact is your usually numeric who, what, where, when, why, or how. The dimension represents the more detail, the flavor around the specific event. And we use appropriate slowly changing dimension types. So one of the big things here is you have one and only one process to write the data. This is, I liken the Kimball-style data warehousing rules to gremlins, where you can't feed them after midnight, you can't get them wet, definitely don't do that, otherwise you have problems. And that's the same for the Kimball-style warehouse. If you treat it correctly, if you follow all the rules, everything's great. If you don't, you have big problems. Next up, overnormalization, not a real thing. Get out of here. What people tend to see as overnormalization is usually one of two things. Number one, you're trying to remove legitimate business flexibility. Going back to that symmetric constraint. If you have a symmetric constraint, yeah, I can break that out into 3 tables. If I don't have a symmetric constraint, usually I don't have one, I need to keep this as 3 columns. 1 table, 3 columns. It's not denormalized. That's the appropriate level. I can't break it down further. The other one is lossy decomposition and phantom rows. In other words, you're doing it wrong and you end up with bad results. That's not a problem of normalization. That's a problem of doing it wrong. So it's improper implementation. Now for denormalization. Normalization has very specific rules that tell you where you're at, how you get to the next level. I am in first normal form. I am in Boyce-Codd normal form. I am in elemental key normal form. With denormalization, however, we don't have denormalized form 1, denormalized form 2. I'm in denormalized form 6. There's no such thing as that. The denormalization is not a set of logical rules. And with denormalization, we can't tell you to what extent. What methods do we use to denormalize? Is this model sufficiently denormalized? Has my data model been denormalized correctly? There is no rule of denormalization. It is instead go willy-nilly and hope that things work out appropriately.
This solves business rules.
To solve business rules, no. So that goes back to this point here that business rules have to be taken into consideration with normalization. And if you are not taking those into consideration, it's not like you're over-normalizing or that you need to denormalize. It's that you're not paying attention to reality. Your model should map as closely to reality as possible. So if your business rule says that we need to collect this information in a particular, we need to collect some particular set of info. We need,
Or extract it out of what's called the regular table, and they call it D&L. Now, getting ready to get into that to see exactly what the heck is in those tables, but that's what it's calling D&L.
okay,
Denormalized data.
all right, so
This is interesting, go ahead.
yeah, either you are entering into a den of iniquity, or yeah, that's my first inclination. Now, you've also mentioned that there's some really old databases there, and a point in fairness is that if your database was created back in 1996 or 1990 or 1985 or whatever, if it's a really old database, you had to deal with hardware of that time, and hardware of that time made it a lot more difficult to follow these rules appropriately. So we took measures that were necessary to solve problems, knowing that, yeah, it's technically not the right answer, but it's the answer I need. And that was the difference between a logical model that was the theoretical right answer and the physical model that was the model that will actually let me get my job done in time.
I think that's what I'm going to run into, but I need to understand all this to be able to go back to the base table to see what is really needed in these D&Ls and where they ship it around to the reporting sites.
Yeah, and you may find out that things get really weird in there. That it's just that was a place where all the rules get avoided, and so
It was hardware constraints.
right. Yeah, so Anders has some stuff that forced running. You only need one table and two columns for any application: a record ID and data in XML format. Anders, get with the program. It's JSON format now. SQL in 98 could only do 12 joins in a query, and you could not get around it using views.
This was access database. Started as an access database.
So this started as access. Wasn't even SQL. Okay, so started with access, which was even more limiting. And yeah, there are limitations like this. Now, today, fewer limitations like that, but if you have enough tables that you're joining together, you can end up with a problem. I would also ask the question of, at some point, why are you joining so many tables together to get that information? And wondering if the data model is appropriate and the queries that you're getting are appropriate. But that's, again, getting into, now we have to talk very specific circumstances. So with denormalization, there's no hard and fast rules of what is denormalization. But I don't want to make it sound like it's never appropriate. To increase redundancy, it can be okay when it's needed, like data warehousing. Data warehousing is built on the idea that I can improve performance of queries, and I can make it easier for business users to access my database by introducing redundancy. The whole point of the star schema is I want to make this so that business users can access data in an appropriate fashion without it taking forever. They shouldn't have to learn how to write complex SQL statements. They shouldn't have to learn all of these rules. They just want to know, how do I get the data to solve my problems? Denormalization, however, if it adds invalid design ideas back in, if you break out of Boyce-Codd Normal Form, if you break out of Fifth Normal Form, we would generally want to avoid this. Adding redundancy, okay. But if we're bringing back the ability to have update anomalies, to have phantom rows, to have these other things, that's what I want to avoid. And normalization is not everything about relational design. It is one part of relational design. Join dependencies, functional dependencies, those are not the only types of dependencies. There are other constraints that exist as well in this world, and normalization doesn't handle those. So normalization is necessary but not sufficient for appropriate relational design. Also, there is no single answer of this is how you get into Fifth Normal Form. There can be multiple ways to break out into 5NF, and there's no formal guidance on which to choose. You could have several possibilities, and the answer is pick one. My third point here, applying academic advice to practical circumstances is not always a direct mapping. It is very easy for ivory tower me to say, follow these rules and everything is fine. When rubber meets the road, it gets a lot more difficult. And I understand that. But normalization is explicitly about the logical model, not the physical model. If you say indexes are breaking the rules of normalization, yes, that is correct, but indexes are strictly a physical model implementation. They're not a concept of the logical model. So we focus on that logical model. We apply as much as we can to the physical model, to the practical implementation. We try to have this mapping be as close as possible because that logical model guarantees us nice things if we follow it. So as we wrap things up, this has been a look at normalization from a mostly academic perspective. It can be a complicated topic. Hopefully I've kept it fairly reasonable, that line between formally correct and actually able to explain to people, especially given that I don't have a whole semester to do this. So if you do want to learn more, you can grab the slides at csmore.info/on/dbdesign. That's where you can get these slides. That's where you can get more information. If you have any questions afterwards, please do feel free to email me, hit me up on Twitter, talk to me on Meetup. Don't throw a brick through my window. I definitely do not subscribe to Brickogram. And if you want to pay me money to have me yell at people, I have a link for that as well. So with that, I want to say thank you so much. All right. And before we sign off, are there any questions? Yes?
So these sets of rules that follow, is it for when you were trying to make a data set yourself or when you're starting out, or is he's dealing with some old legacy data sets that need to be migrated to an area that doesn't have the hardware constraints?
Yeah, okay, so the question is, normalization, is that more a thing for greenfield development, for brand new designs, or is it something that you can go back and apply to existing solutions? The answer is you can and perhaps should apply it to existing solutions, but what you'll end up with is my logical model, my physical model are very different. Physical model is really hard to change. Databases are hard to change because applications depend on them. The data was stored in a very specific way. Translating that data model can take a lot of time, a lot of custom effort, and you may not be able to get exactly the shape of the data that you ideally want because we went down this road for so long. So you may not be able to apply all of that logical model to the physical model, but you can still at least try to mentally reverse out what is existing there, where there are deficiencies, where there are differences from normalization, and at least help understand why do these deficiencies exist? Why do these differences exist at least? And can we do anything about them? The answer oftentimes will be no. Deal with it. It's been there for 15 years. Suck it up. But it at least can help understand why is it that we are having these problems? Then you're able to say, here is why, and now in a future system, I might be able to fix that. Or I might be able to convince a product manager that it's worth the effort to make this fix here because the data model is causing these problems. But what it ends up being is typically a very complex effort. Only do it where it's needed in existing applications. Yeah, Anders, I'd say for implementation, like if you're making changes, yeah, do it where it's needed. If your company, like your application is able to deal with the inefficiency, kind of just say, so be it, and then don't do that next time. But I'd say at least have the data model, have the logical model, have that understanding of here's what it would look like if, knowing what I know now about the business rules, about the code implementation, about all this stuff, here's what I really would have done. And having that logical model can help you in the future. It can help you if you ever get a chance to make a major change. So that's the long-winded version. And I think we're going to cut it from here, so I'm going to go off stream. It took me 2 weeks to remodel one app, 3 months to write and test the ETL. I believe that. The modeling is challenging. It's academically challenging, but ultimately logical. It's a logic problem. It's not I have to spend 90 hours rewriting 1,200 stored procedures problem. So, yeah, that can happen. But we're going to wrap things up for tonight. I want to say again, thank you, everybody. And remember, next Tuesday, we're back online only. We are going to have somebody talking about something, but I don't have Meetup up. Check that out, meetup.com/TriPASS. You can register for our event next week. It is a good one. I remember it's a good one. I just can't remember who's presenting or what the topic is, which makes it sound like I'm just bloviating, but really it was good. So check that out, and we'll be back in person again next month, so come on down if you're in the area. And until we see each other again, everybody. So yeah, actually, sorry, one last thing. I think I mentioned it at the top, but if you are in the Raleigh-Durham area and you are looking for a job and you have experience with SQL Server Integration Services, you want to do ETL-related work, send me a message. I can pass it along to the folks at Tech Systems who are currently hiring for a position. Sound like a good enough picture? You want to add anything else?
Yeah, I mean, it's just with the North Carolina Housing Finance Agency. They're helping with affordable living here in North Carolina. So if someone's got around 5 years of experience, yeah.
All right. So yeah, 5 years of experience working in affordable housing. There's a semicolon in there, so it's 5 years of experience with integration services, with SQL Server, with that kind of stuff, ETL processes. The job is with affordable housing in North Carolina. So message me if you're interested. I can hook you up. And anybody else? Thank you. All right. So till we see each other again, everyone, take care.